Okay, hello everyone. Welcome to the presentation titled Planning and Learning in Automated Driving. My name is Zlatan Ajanovic and I will present you the work done here tonight. So, the outline of the presentation is as we first go through introduction. I will just give you the short introduction to all of this work, the background, how the work was done, and in which framework is it done. Then we will go to the problem statement. So, what is a general problem, and also some idealistic problems which are related to this class of problems. Then I will give you a short overview, very short overview of planning and learning methods in general, just to give you intro that for people who are not familiar with these methods. And then we will go through examples. So we will go first to search-based optimal motion planning example for automated driving, and then example of a combined planning and learning approach. At the end, we will shortly conclude everything. Yeah. So, introduction. The work done here was mainly done in the ITEAM project, which is Marie Sklodowska-Curie Actions project financed by European Commission. I was a Marie Curie fellow at Virtual Vehicle Research Center, where I'm still working, and I did my PhD at the Institute for Automation and Control with supervisor Professor Martin Horn. Also, there was a lot of collaboration through this work with many colleagues, mainly from AVL, from University of Sarajevo, and from TU Delft and Volvo Cars in Sweden. So the general goal is that to achieve superhuman autonomous vehicle. So to develop superhuman autonomous vehicle, this means that we want to achieve better driving performance than human drivers in terms of safety, efficiency, and comfort. The vehicle should operate independently in all conditions human drivers can operate, and it has use case problem specific vehicle dynamics, environment, and performance measures. So depending on which exactly use case of this autonomous vehicle, because it's autonomous vehicle in general, it's quite wide topic. In different use cases, for example, drifting or high performance driving or energy efficient driving and regular automated driving, highway driving, and so on. There are specific vehicle dynamics requirements, different environment, and also performance measure. In this work, the focus is on vehicle intelligence, so only on decision making and control problem, and not perception problem, and so on. So autonomous vehicle actually can be considered as intelligent agent. So more or less, we have in the literature of AI and in general in AI literature term intelligent agent, and this can be there is an agent which interacts with environment, and this can be represented described formally using Markov decision process. And what we have is agent operating in some environment, and the agent is some kind of learner or decision maker. So depending which methods do we use, is it learning or pure planning methods? And the environment there is which everything but agent interacts with. So agent interacts with this environment, and this environment provides agent some kind of feedback, and the feedback is, as we will see, represented in terms of reward and state. And state captures all relevant information from the history. So if we have information about the state, we can throw out all the history from before and just keep this state information. And the decision which agent makes, for example, based on learning or planning, is called action. So this is how agent interacts with environment, and the goal of the intelligent agent is to maximize the cumulative reward in long run. So if we are in some state st now, we want to, in the long run, actually to get all of these all of the to maximize the cumulative reward of all of these uh, rewards which we will get in the future steps. This is not so easy problem, and uh, we will see different methods to achieve it. There are also different possibilities to describe a system. If system is, for example, not stochastic, or if it's fully deterministic, we can also, for example, formulate it as optimal control problem. So there are many different examples of the intelligent agent. So it can be finding a path in a maze, or playing a backgammon game, or playing Go game, or balancing the pole on this moving base, and also automated driving. So now we come to the planning and learning method. So we want to I want to provide you some basic information about the planning and learning, and just to get everyone familiar with this. There are not so many details, let's say, but I think it's enough to get the full intuition. So actually, planning and learning are all solving this the same problem actually. So we have an intelligent agent, and we want to achieve some kind of intelligent behavior of the agent. What planning, there are two actually basic ideas. So it's based on value function as a key intermediate step toward improving the policy. So these are state space planning methods, and they need some kind of value function which represents this long-term cumulative reward. And what they do is they compute value functions by updates or backups operation applied to simulated experience. So we have we get some simulated experience. We go through the search space, and then we update this value function accordingly to get the final policy. And the goal is to by as we see on this figure, by using a model and applying a planning method, that we get some kind of value function or a policy. And learning is similar to planning. The only thing is that learning uses a real experience, and learning actually does not require the model in general, because it uses real experience. So what we have here, if we have some acting based on the policy, or also based on some exploration policy, uh, we get some experience, and then we can do direct reinforcement learning. What is model-based reinforcement learning is, we can also, what is called model-based reinforcement learning, we can also learn the model and then use model for planning to get the policy. And actually everything is in this circle, and how do we go around this circle? So as we said, there are different methods for the getting the solution. And what it looks like is that when we look at the this problem, what happens is that usually we can represent it as a tree. So we have some kind of initial state. The black one represents the action. We have some action, and then based on this action, if it's deterministic environment, we will have directly one additional state. But if it's not deterministic environment, if there is stochastic environment, or if there is some other agent, also, for example, in a game of chess, if there is some other agent in the game, we can get more than one, actually a different state for one action. And there can be some kind of distribution probability on which state do we end up. And the goal is actually to find what is the best way to traverse or to get the action. So what we want to achieve in the one step is we just want to achieve one of these actions. Should we take this action or this action from initial state? But sometimes this is not possible to get this long-term reward. So what we do is we need some kind of planning which goes through the tree and gets the idea of which branches of a tree are more favorable than others. When we look on a tree itself and the methods, we have a width and depth of a tree. So we see that width represents the how many actions do we have, let's say, on the each step, and also the depth represents how much do we need to go deep into this tree. Temporal difference learning is only actually very limited to let's say one step in depth. So we just do one action, and then based on the outcome of this action, we apply this to value learning. But also it's a very narrow width because we just take action and we don't look other possible actions. On the other side, there is a dynamic programming which can take the full width. So it has to take to get optimal solution by dynamic programming. The pure dynamic programming, we need to take the full width, and also we usually go through the whole space. So to get the full value, we go through the whole space. But also there are different methods like value iteration and policy iteration which only go for one step. And what advantage of dynamic programming is that we just go through one step, and we reuse results of previous steps. So if we have a value function, for example, for this stage here, we to get this value function here, we just take one step. The other methods also are Monte Carlo approaches. For example, famous is AlphaGo, which used Monte Carlo tree search to traverse and go very deeply actually into the tree, and even let's say 20, 30, I don't know exactly how many steps. So for playing, let's say, the game against the human, it needs to look many steps in future. And what it does is it doesn't go it goes, let's say, it has a different policy for rollout policy and selection, node selection, and then it selects which nodes is the most promising for expanding to get and expands it. And on the worst case is actually exhaustive search. So exhaustive search searches through the whole space and gets the solution for the problem. The best way, let's say, if we have a computational resources, is to do exhaustive search. But the problem is that if there are multi-dimensional space, if there are many branching factors, so if width is high, so if here we have only 2 branches, but if we have let's say, as in game of Go, 200 branches, it easily gets infeasible to find it in a real time. So we need some kind of approximate methods. And what the advantage is that actually for some problems we can use some methods, and for some problems we need additional methods. So in many cases, what happens is that we have let's say, as we look here, these states start repeating itself, let's say. So we can have that states starts to repeat itself. So for example, problems of let's say, optimal control, where we want to plan velocity of a vehicle or something like this, we get the repeating states. So we can have a, let's say, graph like this. This is a acyclic graph. So it's directed into the side. So if we have a, let's say, time on one axis, the some other state variable on another axis, what we usually have is we can have a, let's say, one final goal state. So we have a goal state which we want to achieve, and initial state which we start from. And then how do we go through this state space actually is determined by which methods do we use. So for example, if we use backward dynamic programming, we would go backward from this state. So we will look at the all states here, then we go one step back, look all of these, then we go one step back, look all of these by reusing the results here, and so on until we come to the initial state, and then we take the optimal action. Other way is, for example, using A star heuristic search. We just focus and we use additional information which is called heuristic function, which guides our search and to avoid searching in the whole search space. And then we, based on the let's say we based on the results of the first state, we choose the next one and we search until we find the solution. So how does it look? You can see on this animation, you can neglect this part here, but you see that backward dynamic programming, we go from a back, and forward dynamic programming, we go from a start. And A star actually, so I can go again. So you see that A star search goes where more promising regions are, and it doesn't search the whole search space. And then this is important because then we will use these ideas of different search spaces and different methods to get very efficient actually algorithms. So now we come to the example of automated driving, which I want to present you. So first, to achieve this superhuman autonomous vehicle, there are many actually different use cases. Only 3 are mentioned here. These are which I tackled through my research. But there are many more, and we need to solve all of them actually to have the superhuman autonomous vehicle which operates in all the conditions where human driver operates. I used also different methods and learning, planning, and control methods. The control is related to dynamical system and how to deal with continuous dynamic system. As we saw previously, we had discretized state space, but we also need to sometimes consider continuous state space of the system. So what the first example which we will see is automated driving in regular urban traffic based on planning and control. So we have this problem, and we will look at this toy example. So there is autonomous vehicle which we control, so marked in yellow, and there is a purple vehicle in front of it, and there is a traffic light, and these vehicles are approaching the traffic light. To have this dynamic problem, to have it as a static, and to be able to actually plan to find the best solution for this problem, we can augment this state. So one with time. So one axis is S, which is distance along the road. The other one is L, which is lateral motion on the road, and then the third one is time. And then the traffic light becomes some region, represents obstacle as a region in this three-dimensional space. So we see here that after some time, the traffic light turns yellow and then turns red. Then the other vehicle, which is in front of us, we use some method to predict. In this case, we just predict that it will continue with constant velocity, and we see that this vehicle represents some region which is moving in front of us. So the vehicle occupies this region, and we see here that it passes the yellow light before it passes the traffic light before it turns yellow. And then for ego vehicle, we need to plan actually the trajectory. So as a sequence of these states, which doesn't collide with any of these obstacles. So it's more or less the same problem as finding the path in the maze. Exactly the same problem theoretically. It's just the maze is, let's say, higher dimensional, and also we have a continuous space. So we have a continuous search space, and we need to solve it with some other method. So to avoid the continuous space problem, we can generate motion primitives which represent different actions of the vehicle. So we have here longitudinal motion variant. So we can sample different accelerations of a vehicle. So if we have some initial velocity shown here, so this is again S and T graph, and initial velocity of the vehicle represents the gradient in this point. We see that there is some initial velocity of the vehicle, and based on the actions, we see that in this case, vehicle accelerates the maximum, here accelerates a little bit less, and here keeps constant velocity, and here the vehicle slows down, and here is the maximum deceleration of the vehicle. So these are the longitudinal motion variants which we generate, and then we generate different lateral motion variants. So lateral motion variants we generate based on the lane change right, lane stay in the lane, and lane change left. And we approximate this by a hybrid system, let's say. So we neglect a bit the full dynamics of the lane change, but we model this also with time of lane change. So we know that it's not instantaneous, so it cannot the lane cannot be changed instantaneously, but we have some kind of uh, time needed for a full lane change. And then combining these motion primitives, we can get motion primitives, different motion primitives. Here we have a set of motion primitives for lane change left, and here we have a set of motion primitives for keeping the lane. And then based on this, we use a search-based optimal motion planning. So we develop this algorithm based on the heuristic search, motion primitives, and also some kind of heuristics to plan in this complex space very efficiently. So a trajectory of the system is built by concatenating motion primitives. So this provides us that the system is dynamically feasible. So what means that when we have initial velocity here, we take it as a part of the state and initial condition for future action. So then we have it dynamically feasible. Then we plan until any of the trajectory reaches distance or time horizon. So if we look at this figure here, we search until we reach some of the time or distance horizon, and then when we find, let's say, the trajectory which keeps our vehicle collision free for, let's say, next 10 seconds or next 200 meters, we are finished with this plan, and then we can take the first action and in MPC approach, and then we take this first action and execute it, or we take the planned trajectory and provide it as a plan for the following. And we use a hybrid A star for practically searching in continuous space. So the hybrid A star is one variant of A star heuristic search, where we can use the to search in continuous space and keep all of these continuous variables still without rounding them to the grid. And we use relaxation-based heuristics for guiding the search. So we use actually dynamic programming to solve the simpler problem, and then use this solution for the future planning in the search-based optimal motion planning. And if timeout is reached, so it means that if we have some set timeout, and if we didn't find solution for the for the which reaches the distance or time horizon, we use the, let's say, the longest plan which we have so far. So how does this work in reality? So we have the example, a little bit more complex example as shown before. So there's a ego vehicle is white in this case. So this is our vehicle which we control, and all of these are different vehicles driving around us. So we see that there is a traffic light here, and now we have also again this T and S plane. So this is generally three-dimensional space, but we show here SL projection, and here we show actually this is SL slice, so only in the initial state what is happening here, not the projection, and we have here ST projection of all of these vehicle states in the future, how we predict they will be. So we see here that the initial state of the ego vehicle, it has some initial velocity, and this traffic light here is turning after, let's say, 12 or 12 and a half seconds, it will turn yellow and then turn red. And we see that the red vehicle, which is in front of us, is this one. So if it continues driving the same velocity, it will be this one, and it will be the last one catching the the green light, and then the light will turn yellow. So it's quite complex and challenging scenario, because the ego vehicle has to overtake this vehicle. So we see here that the ego vehicle speeds up, catches this vehicle. So we see here that the ego vehicle actually goes into this gap here, so catches the vehicle, and somewhere here when it catches, then it starts to changing the lane. So it changes lane left, and then during this time it changes lane and then speeds up and passes actually the red vehicle. So this red vehicle, which at this moment it will be here somewhere, so it will pass this. So this ego vehicle will pass this red vehicle somewhere here. And how this works in animation, we see here that, okay, the ego vehicle plans, it plans and now changes lane, it changes lane, and then it passes the red vehicle, and all other vehicle actually stay behind, so they cannot catch the green light. And again, same, the vehicle overtakes the red vehicle and then passes the red vehicle. And in background, what happens is that we actually use heuristic search method. So this SBOMP algorithm which we developed to find actually this optimal solution. So we see that we explore the space, so search space, until we find solution which goes either to distance or time horizon, and then we found it now, and then we execute for one part, and then we again search for the solution until we reach distance or time horizon. And this happens in background with very high frequency, so around 100 milliseconds per step. So this is not interesting. We also validated this in the simulation, driving simulator, and on the proving ground, but I will skip this and go into a different example. So the other example is performance autonomous driving, where we use different models to achieve actually more dynamical driving. So we want to push vehicle to the limits and some kind of drifting maneuvers. So what we have here is that we have a vehicle which is represented by higher dimensional system now. So node, which represents the state. So the state of the system is in node. We have a x, y position. We have a yaw rate. So this is orientation of a vehicle. We have a velocity of a vehicle. We have a side slip angle. So these are vehicle dynamic states, and we have a yaw rate. So you see that it's quite already high dimensional. So we have a 6 dimensions already. And what we have here is that it's very complex actually space to search in. So what we did is we simplified this and we use different motion primitives. Some are for semi-linearized single track model, and we sample that in the some regions of the state, and the other ones are for drifting. And by approximating the all actions of the system into these smaller sets of actions, we can actually get a quite good result. So same as before, we generate from initial state, we generate different motion primitives, and then again we remove which are colliding with the or which are out of the road, so they are colliding, let's say, with the obstacle. Then we select new node to expand, we expand it, and iteratively when we do like this using motion primitives, we get the full trajectory for the system. And this is how it looks like. So we have the full plan of the system for some horizon. You see here the full plan, what the vehicle plans, but it only takes the initial plan and then replans again in the MPC style. And in background, what is happening for each of these plans to come, we actually have this tree search, and we use heuristic search to find the solution and to find one feasible solution. So what is the main problem actually with the planning is actually computational complexity. So what happens is that we usually do is that we need to search very let's say many states to get the final plan. So it can happen that we have let's say 200 branches, and if we have a 10 states or even more, we can easily just scale, and because of the curse of dimensionality, we can get into the that we have a more let's say states to search than the stars in the universe. So it's quite easy to. And also the other problem is that usually we assume actually for planning that we have available models. So sometimes it happens that we don't have available models, so then we need to go into learning methods. So what we have also done here is also with colleagues from AVL with Halil Beglerovic, we did here that we combine learning and planning. So we can use planning to generate some data to improve future planning, let's say. So the main idea is that we can actually learn value function by and using it as a heuristic function in the search. So what happens is that if we have a value function of a system, which represents let's a long-term reward which we will get, we actually ideally we can use it greedy, so we just go in direction which maximizes our value function. But the problem is due to the noise of the value function, we can get not so good behavior. By using the planning, we can avoid this noise because we have more stages, and then this noise cancels out because we have more noises. So even if there is on one stage some noise which directs search into other direction, still this is not executed. So still this is only in the planning phase, so inside of the, let's say, agents in internal simulator, and in the second third stage it will be corrected, this action, if it's not leading to the right direction. So if we have this value function, then we know that we can also use it as a heuristic function in a star search. But also what we can use it, we can use planning algorithm. So for example, a star search with existing heuristic function which we have to go through the search space, and also to generate data which we can use for the learning of the value function. So what we use in this work is that based on the premise that for learning of the value function, it is more beneficial to explore states in the neighborhood of the optimal policy path or policy than elsewhere in the state space, as the agent will spend most of the time in the neighborhood of the optimal plan. So what this means is that actually first we have a different planning problem. So and we can generate different scenarios. So we usually have our algorithm running in different scenarios, and we have more scenarios, let's say, and all of these scenarios, each of these actually scenarios has a quite large state space. So we can either focus on exploring fully many smaller number of the scenarios, or we can focus on getting into more scenarios. So we go into more scenarios, and we explore the neighborhood of the optimal path. What other people actually, this is a trend in last, let's say, 2 years, that people use planning to learn value function and to improve planning. What others did, actually they just uh, they used either full exploration of the state space. So this means that they have an exhaustive search on a smaller number of the examples, or they just use solution. So they just use a result. So if we remember the case of automated driving, instead of the whole let's say the whole tree, they just use the solution path, and they throw out all the rest of the work. What we did here is actually we combined this, and we found the, let's say, something in between. And what helps us here is that we usually have learning approaches which provide which have challenge to provide guarantees on performance, and also to have safe exploration usually. And they deal problematically with long-term rewards. But also planning algorithms are rather slow in high-dimensional spaces, as efficiency of heuristic search depends on the quality of the heuristic function. So we need to improve this heuristic function. And in this work, we developed this novel approach for efficient and systematic exploration of the models based on the backward and prolonged heuristic search. So what we do is we start from a final state, and we also, so this means this backward, and we also prolong a search until we have a higher region around the state. And you will see in the following figures how does it look like. So this ensures that only interesting nodes are explored. So we explore only nodes in the neighborhood of the optimal path, and also that all explored nodes are used for value function learning. So this is a difference to the state of the art what other people were doing. And this is somehow systematic data set generation. So for example, optimal solutions for supervised learning of optimal behavior. So we use this planning and the model, and we generate data set, and then we can use supervised learning to learn this value function offline, and then use it online much faster than the pure planning with some worse heuristic function. Okay. And how does it work? So we have in the center this dataset generation. So we use this prolonged heuristic search for dataset generation. So it's same as before heuristic search. The only thing is that we keep the exploration, and we keep even when we find path. So if you look here, how does it work? This is the grid vault problem. So this is kind of a maze which we generate randomly. So these are maze which have some starting and starting and a final go node. So you see here the positions are starting and a final, and we need to find a path from start to goal which doesn't go on these black cells. So this is a kind of a maze. And what we do with heuristic search and like A star search, for example, we search using, let's say, Euclidean distance heuristics, and we find some path. So we find a path which is marked in green, and we explore this part here. So these are all nodes which we explored during this planning process. As I mentioned before, what other people in this community did previously, they throw out either they throw out all of these results from the red nodes, export and just take the green nodes, or they also search the whole space. So this would mean that in this grid they search the whole space using some dynamic programming like or Dijkstra search. And what is problematic here is that if we have unlimited search space, so for example, if there are no limits here, we would spend infinitely to search here. So it's not efficient. What we did here is we look when we find solution. So we on the right side, so we find the solution, and then we keep exploring for some more time. So we keep, let's say, for 2 or 3 times longer, so that we get 2 or 3. So we keep exploring until we find 2 or 3 times more, let's say, the nodes. So this helps that, as you see here in the first vanilla shortest path problem, we don't have any, actually, in data set, we don't have any nodes which are showing this very close to the optimal path. So if even in execution, if something happens and if a little bit due to the noise or something else, agent drifts a bit off optimal path, it will not have any, let's say, representatives in the data sets, so on which value function is based to get it back to the optimal path. And with this prolonged search, we get more of these. So this is where prolonged comes from, and backward comes that we search from a goal, so that we can use all of these, actually all of the states which are explored, because all of them lead to the goal. So we can use all of them and we don't throw them away, and we can use them as a data set for value function learning. And then the other feature of this approach is we use a loss function, which is kind of asymmetric. So because of the A-star algorithm which we use, we want to always underestimate value function, because of the feature of A-star, that if heuristic function is underestimating cost to go, we get the optimal solution. So we penalize more, let's say, positive. We penalize more overestimates than underestimates of the value function. And when we use heuristic function in the search, so we also limit it. So this represents saturation. So when we learn based on the model architecture and supervised learning, when we learn the value function which represents the cost to go, we limit it with admissible heuristics. So we have admissible heuristics. For example, in the shortest path problem, it would be Euclidean search, and we limit these with some epsilon bound. So we know that our machine learning heuristic function, so value function which we learn, should be higher than higher than admissible heuristic which we have, because admissible heuristic which we have is already underestimating cost to go, but we want that it's closer to the real value than and not underestimate too much. And also we limit it on the other side with epsilon, such that it doesn't overestimate too much, and this epsilon helps us to have a guarantees on optimality. So this means that our optimal solution is always epsilon times, at maximum epsilon times larger than the optimal solution. And the results here, so we used actually compared the results using vanilla with other state-of-the-art solutions. So we just compared it to learning with vanilla shortest path problem without this prolonged heuristic search. And what we get here is training and test loss for the prolonged heuristic search is this one, and we see that it kind of converges. They both converges. This converges faster, and also it is less overfitting than other one. We see in the vanilla case that there's much more overfitting than in the case of the prolonged heuristic search. And when we apply this to the planning, so the goal was, as we said, that we use this learned value function again in planning to have a faster planning. We see here that when we use admissible heuristics on the left, we explore much larger space than when we explore using machine learning heuristics. So these are the let's say two example, and what our plan was to use this on the automated driving. This is a work in progress, so we want to apply this approach to very complex automated driving problem as planning problem, as we saw earlier. And we can represent each of these states. For example, state here, we can represent it as a 3D grid like this, and state here we can represent it as a 3D grid like this. So as a conclusion, these are very narrow samples of all what is there with combination of planning and learning, and I think this is quite promising field, and many research is now uh, uh, happening in this field. What we presented is general motion planning framework, search-based optimal motion planning, and it's scalable to different use cases for automated driving. Still, there is a computational performance problem. So in this example, it's working on the limits, but if we want to go into more features, into extending more vehicle dynamics and having more driving features, then it gets slow. So that's why we need some kind of approximate methods. And we also presented the work on the novel approach for the model exploration for value function learning, which is one of the approach which could be learned. Yeah. So thank you for your attention, and I hope I'm in time. So let me check the Herbert. Can you hear me? So I think we